Right, hey everyone, this is Nicholas Brown and I'm just going to undergo a quick demonstration of how I assembled the 736 Lumen lantern project. Well, not just a lantern, but it's intended for a ceiling lamp, but it's not in a fixture as yet. So as you can see, it's kind of in pieces now, but it's a dimmable 70-watt equivalent lamp. So I'll just name the parts. This is a CPU heatsink I had laying around. I use it to cool the LEDs, which get very hot sometimes. These LEDs are 368 lumens each, and the fan isn't connected at the moment. I haven't needed it yet, although I'm gonna set it up anyway, just in case it gets really hot. And this is a Panasonic NCR 18650B lithium ion battery, and this is a Texas Instruments MSP430 G2553 microcontroller kit called a Launchpad. So that's the USB port, that's an MCU itself on the Launchpad board. Anyway, underneath the microcontroller's board is 3 Panasonic NCR 18650B lithium ion cells. They are 12 watt hours each. This one here on the outside is wired separately to power the microcontroller. Right, so basically I just have a positive and a negative wire coming from the 18650 cells, these two transparent wires here, and that powers the LEDs and will eventually power the fan. So I'll just can't do a full assembly, so that's why I left some things in place already. The ground wire, forgive me, I ran out of black jumper wires, and the VCC wire, which powers the Launchpad. The Launchpad is powered up now, and this is the control wire which connects to the MOSFET transistor's gate. So let me just give you a quick look at the transistor. This is an IRF520 MOSFET transistor. MOSFET means metal oxide semiconductor field effect transistor. So in the order from left to right, the pins are called gate, drain, and source. Source is connected directly to ground. In the case of this circuit, the ground, I should have said negative terminal of the battery pack. By the way, it's a 12.6 volt lithium ion battery pack in there, and drain is connected to the negative terminal of the load, which is the lamp itself, the LEDs. So it's just a little heatsink to keep the transistor cool. It gets a bit warm sometimes. So I'm just going to hook up the the control wire now to the PWM. So basically, before I continue, the control wire connects the control wire is connected to the transistor's gate, because the transistor's gate is used to control the transistor and all the current passing through it. So you can consider the gate almost like the switcher. If you supply a small current voltage to the gate, rather, it will switch the transistor on and allow electric current to pass through it. So that's how I utilize PWM to achieve this. Right? So pin 1.2 is what I'm going to plug the control wire into, because pin 1.2 is what I set as a PWM output. So just a quick overview of PWM. PWM involves switching a DC electric current on and off many times per second, and modulating the amount of time, modulating the on time of the PWM signal, of the Yeah, it can be called a PWM signal, but to clarify, it just modulates the percentage of the time that the power is on to vary the brightness of the LED. Right, so for example, if the duty cycle is set to 50%, that means that the power will be on 50% of the time and it will be off 50% of the time. But it's not going to look like the LED is blinking because it's switching so fast. Alright, so the control wire is connected, and now I will connect the transistor's drain to the other ground terminal on the Launchpad, and that is basically it. I think I'm just going to tuck this transistor back down in there for less clutter. Right, so I'm not sure if you'll be able to see. Let me just turn on the lamp. Okay, I just held it down for too long. So that was, oh yeah, so I think that is 20% brightness now. It has 10 brightness levels. So at the lowest brightness level, which is 10%, it only consumes 0.7 watts. So let me just turn it on. So you press a button to turn it up, and once you reach the maximum brightness and press it again, it will just shut off. So let me set it to minimum. Right. So the minimum actually turned out to be quite bright because many LEDs are actually more efficient at lower brightness levels, meaning if we use a smaller fraction of their capacity. So that's cool. Anyway, so this will be encased in a decent looking lighting fixture eventually, but I thought I'd do this in case you wanted a simple starter project, or or just an idea as to how to get started with PWM, because this can easily be applied to automotive LED or even incandescent lamps. I would recommend LED for this, and so that way you can get extremely bright bulbs and turn them down to a normal level and then turn them up if you're going off-road, for example. So that's a convenient project, or if you're making a flashlight, your own lantern, anything whatsoever. So this concept is supposed to enable you to there are two purposes at this concept. One is to make it easy to solar power LEDs with dimmers, because to be honest, this is an entirely DC setup, and solar systems operate on DC internally, 12 volts DC. This is 12 volts DC, so it's actually very cheap and very convenient to hook it up directly to the internals of a solar system. So you will have to use an inverter plus an AC to DC converter in every LED bulb, etc. So the way things are conventionally done is extremely wasteful and expensive. So LEDs have the potential to be far cheaper, and solar systems do have the potential to save a lot of money. Nearly every LED TV, actually every LED TV operates on DC internally. Every computer operates on DC internally. So I mean, plus every tablet, phone, and a number of other electronic appliances, your stereo, your receiver, etc., they operate on DC. So, and in most cases 12 volts DC, some 5, so a lot of money could be saved by emitting those huge AC transformers and the AC to DC converters, which are rectifiers. So I think I can wrap this up now. So as I showed you, transistor only needs 3 wires for gate, drain, and source. Gate is control. I'm using drain as the output in this case. Well, the load connection, and source is what enables me to connect to source is connected directly to the battery's negative terminal, so that I can use a transistor to connect or disconnect the LED's negative terminal from the battery's negative terminal, because disconnecting breaks the circuit and shuts off the LED. Connecting it makes the circuit and turns the LED back on. So switching that on and off many times per second, it's thousands of times per second actually, achieves the PWM effect, and that's how you can vary the brightness, because as you can see, it doesn't appear to be flickering or anything, even though it's actually switching on and off thousands of times per second. It's also extremely efficient. PWM is one of the best, well actually no, it is the best dimming technology that I can think of. Because if you're to use voltage regulators or any resistive technologies, like just a potentiometer and a transistor alone, they will burn off quite a bit of your current. So the other purpose of this concept is to demonstrate the integration of battery backup into LED overhead lamps. So this is the type of lamp that's intended to be installed in your ceiling in place of your CFL or any other light bulb. So if there's a power outage, you're not going to end up in darkness, and you won't have to buy a lantern, you won't have to change out your batteries and worry about batteries leaking and damaging your lantern. You'll just continue to enjoy lighting, and you won't have to worry that, and when the power comes back, it will automatically recharge. Anyway, this is Nicholas Brown from Compulsa, and thank you for watching.